Let's take a few minutes and revisit this model that involves the relationship between per capita wine consumption and the death rate due to heart disease. So the list with the per capita wine consumption data is named wine. Store that into list 1, and D rate was the heart disease death rate. That list, D rate, store that into list 2, and then we can create a scatter plot, and we can use zoom 9 to see these data again. So I have my data already in list 1 and list 2. So to set this up as a scatter plot, remember to turn your plot on. Here's the scatter plot option. X is in list 1, that's per capita wine consumption, and then the death rate due to heart disease is in list 2. And if we plus zoom 9, we can see the scatter plot. And again, we can see the negative direction here. We can see that it's a relatively strong relationship, and we had originally modeled this as a linear relationship. So let's actually look at the best fit line. The best fit line is something that we have built before. Here is the predicted heart disease deaths equal to the intercept minus the slope times liters of wine. Again, this was the regression model that we've used in the past. So let's just put it into the y equals menu, and we can see the type of fit that we've got here. So if I press y equals, I'm just going to type in 261 minus 23x. So we can easily see the linear trend, and we can use that linear model to make some predictions. So, for instance, let's predict the number of deaths due to heart disease when per capita wine consumption is 5 liters per year. So we're just going to substitute in the 5. So 261 minus 23 times 5. Go to the home screen. Here we go. We would predict 146 deaths per 100,000 in the population due to heart disease. So that's our prediction. That's our heart disease deaths. But that's our prediction. So, and you can actually see that in the model. So if we go to the graph, if you press the trace button, right now we're tracing the plot, but if you press the up arrow, you'll see that now we're tracing the linear model in y1, and if you type in the 5, that's the x value for which we're trying to make our prediction, it will give you the y value, the prediction of 146. So let's make another prediction. So here, let's predict the number of deaths due to heart disease in a country where per capita wine consumption is 15 liters per year. Now, notice 5 liters per year fit well into the x values that are in our model. Actually, when we used zoom 9, if I press the window, zoom 9 set the x minimum to 0 and the x maximum to close to 10. So there aren't any observations in the data set that are near 15. That, first of all, maybe 15 isn't the best x value that we should be using to make this prediction, but let's make the prediction anyway, and you'll see what the problem is. So 261 minus 23 times 15. Take a look at what this prediction results in. Back to the home screen. Our predicted number of deaths due to heart disease is -84. So not only is this a case of extrapolation, first of all, the prediction isn't reasonable. You can't have a negative number of deaths due to heart disease. But one of the problems is this x value is really far from the actual values of the explanatory variable that's used in this model. We didn't exceed anything around 10. So using such values like this, unreasonable values of x that aren't really close to anything in the model itself, this is called extrapolation. I suppose you could think about it as this x value is extra far from the other x values in the model, and so really this prediction, we shouldn't be surprised that it's nonsense, but it's also nonsense strictly because the prediction can't be negative in this context. So the truth is that the number of deaths due to heart disease at some level, if you look at the model, it seems natural that instead of a linear model, we would expect the number of deaths due to heart disease to actually level off. I mean, they can't forever decrease. So maybe what we need is a different type of a model. So here, maybe a nonlinear model is more appropriate because eventually a downward sloping line will cross the x-axis and it will naturally give negative y values. If those values don't make sense, those are response values here that don't make sense, maybe what we need is a model that's not a straight line, a nonlinear model. So let's try an exponential model. One of the ways that you can remember that this is exponential is because exponential, the x value is in the exponent. So what's really interesting about this exponential model is by applying properties of logarithms, we can take this exponential model and we can transform it into a linear model so that all of the linear regression techniques that we already know, we can reapply in a nonlinear context. So take a look. Here's the basic algebra. So here is our exponential model. Again, I know it's exponential because the exponent is the input, x, the explanatory variable. The y value is the output, that's the response variable. So let's start by taking the common log of both sides of this. So this is a log with a base of 10. When the base is 10, we don't typically write the base. So here, this is the product of a times b to the x. One of our log properties allows us to take the log of this product and separate it into the sum of two logs. So the log of the constant a plus then the log of the base of b to the power x. A second log property that we learn in second year algebra is that this exponent on the base of b, we can actually take this exponent and we can move it in front of the logarithm. So we can rewrite this expression leaving the log of y alone. There's my equation. There's the log of a. This expression we can write as x in front of the logarithm times the log of the base. So all I'm going to do here is then change the order of this expression. So I'm going to leave the log of y alone, the log of a alone, and I'm going to put the log of b in front times the explanatory variable x at the back. So what I want you to see, though, is that this is a linear form. So notice a linear form has an input multiplied to a slope plus a constant, and then it should equal an output. So notice our input is still the explanatory variable x. X is being multiplied by a slope. That slope just happens to be the log of the base b, but this is a constant number. So this is the slope, which is multiplied to x, plus our constant or our intercept, that's the log of a. And then it equals an output, but notice that output is no longer just y, or the response variable, it is the log of y. It's the log of the response variable. So what we've done here is the exponential model has been transformed into a linear model where the explanatory variable is still x, plain x, and the response variable is no longer just y, it's the log of y. So what I want to do, let's actually create the log of our y values. Our y values are stored in list 2. Let's take the log of list 2 and store it into list 3. Let's do that next. So on the calculator, from the home screen, here's the common log button. I'm going to take the log of the response variable that's in list 2, and I'm going to store that into list 3. So next, we've done that on the home screen. Now what we're going to do is take L1. Those are the plain x's, and we're going to plot them against the log of the response variable, the logs of the y values. That's what's in list 3. So we're going to graph x versus the log of y, and we're going to see if that's linear, if that gives us a linear shape. If this gives us a linear shape using x and the log of y, then working backwards through our algebra, what that suggests is that exponential model, y equals a times b to the x, is a good fit, is a good plan. So all we have to do, since we have our scatter plot turned on, we just need to go into the scatter plot. second y equals, and the log of the response variable is in list 3. So L2, I just need to change that to L3. So, and again, I need to press zoom 9. There we go. So understand, when I look at that graph, again, I still see the downward sloping trend, but that definitely looks like a linear pattern or a linear trend. But understand, what we're looking at now is not x versus y, it's x versus log of y. If that's linear, that suggests that the exponential model is a good plan. And not only that, we can use list 1 and list 3 in order to run a linear regression and fit this exponential model. So using what we already know, let's go back to the calculator. So I'm going to go to Stat and Calculate. I like to use linear regression option number 8. So I'm going to scroll down there. Here we go. So the X list, the plain X's, those are in list 1. Now, the Y list, I don't want to use the plain Y's in list 2. What I want to use is the log of Y. That we've saved into list 3. Highlight Calculate, press Enter to bring that command to the home screen, and there we go. So this is our linear model. So notice then, A is our intercept. Our intercept is this expression here. We'll round that to 2.45. That's the intercept. And then here's the slope. The slope right here, we'll just round it to 2 decimal places, negative 0.06. So let's write out our model then. So understand, we have fit a model using the log of y and plain x. So when I write this model, it is the predicted, there's my hat, it's the predicted log of y, or the predicted log of the heart disease deaths. This is equal to my intercept, which is 2.45, plus the slope. The slope is negative 0.06, and that is multiplied to my plain x value. My plain x value from my model is the liters of wine. Now, I know that this is really an exponential model, though, in disguise, because I have plain x for exponential, but I know it's exponential because I'm using the log of the response variable. But this is still a linear model. And understand, using all of the strategies we already know for linear regression, we can interpret the slope. So I want you to use this model, see if you can interpret the slope. See if you can interpret the intercept. See if you can interpret the coefficient of determination. Again, the coefficient of determination, that's r squared. That's something that you can get off of the linear regression output that you should see on your calculator. Here's the coefficient of determination. Here's the correlation coefficient. So something else then I want you to do, on step 7, I want you to graph the residual plot. So to graph the residual plot, something simple to do, if you go to your scatter plot, in order to graph your residual plot, just go into plot number 1, and instead of graphing list 1 and list 3, all you need to do in place of list 3 is go to second stat, bring up your lists. Then I start from the top and I scroll up so that it takes me to the bottom. Here is the list resid, R-E-S-I-D. Those are the residuals. So if you store those residuals into your scatter plot, you can press zoom 9 now to actually see and interpret your residual plot as you're being asked to do in question number 7. And then I want to see if you can use what you know about logarithms and exponential functions. Let's see if you can make a prediction using this new model. That's what step number 8 is about. So the idea here is maybe an exponential model in this situation makes a lot more sense in this context, but by using logarithms, we can turn the exponential model into a linear form so that we can recycle all of the strategies that we already know about linear regression.